If we know what type of equation we're working with or what type of function, and we know what its pattern is going to be in the graph, we can sometimes come up with quicker, shorter ways of graphing them than just simply point plotting. We're going to look at lines in this slide, specifically how to graph them very quickly with slope and y-intercept. Now, if a linear equation or a function is written with y by itself, most functions are written that way, and the other side simplified, as we have in the equation right here, what we would have is the x value being multiplied by the slope of the graph, and the constant term b is going to be the y value of the y-intercept. So what we're given when we have this equation written this way is we're giving the steepness of the line and a particular place where the line goes through, in particular the y-intercept. This can make graphing a line really quick. So again, slope is the steepness, and then the y-intercept is giving us a point. Now let's recall what slope does. One way that people often talk about slope is its rise over run. They say rise because what a slope does is it looks at the change in the y values between the points divided by the change in the x. And the reason they say the change in y is like the rise is because y has to do with vertical change. When you look at the y values of a point, you're thinking about how far you go up or down between those y values. The change in x would be going horizontally. The equation for that, if you ever had 2 points and wanted to calculate the slope, would be to subtract the 2 y values of the points and subtract the 2 x values and then divide them. Notice that the change in y is always on top. So you always want to work with the change in y first, in terms of it being the numerator, and then move on to the change in x when you're graphing the slope. We can use this slope to graph any line very quickly as long as we have one other point, and the y-intercept would be one such point. Let's look at examples. Let's use the technique involving slope and the y-intercept to graph the function f of x equals 3x minus 1. Now this equation is in slope-intercept form because f of x implies that we have y on one side, and then 3x minus 1 is simplified. So comparing that to slope-intercept form, y equals mx plus b, what we have is 3 as the slope, and negative 1 is b, so that means the y-intercept is at 0, negative 1. Don't forget that the b value is just the y value of the y-intercept. So we want to start by graphing the y-intercept. So we're going to graph at 0, negative 1. And then we're going to use the slope to get to more points. The slope, if it's a whole number, can always be written as a fraction by writing it over 1. So I'm going to write the slope as 3 over 1. It's important you write the slope as a fraction because remember the slope is defined as a fraction with rise over run. Now the numerator has to do with that rise component. You're going to go up or you're going to go down, and it's going to be based on the sign of the slope. We're going to go up because this is a positive instead of down. If it were a negative, we would go down. And then 1 means we go across in the denominator because the denominator has to do with horizontal. So we're going to go up 3 and across 1. Now we do that from the point we have. So we already have a point on the graph. We're going to go up 3 from this point. So that takes us up 1, 2, 3 to 2 and across 1. So I will kind of show that in green. I went up 3 units and across 1. You can do that again. Up 3 and across 1 would be another point at 2, 5. So you can use the slope to create the steepness of the line and find new points. Now here's the nice thing. You can also go backward, because we're kind of running out of room as the grid continues. So instead of going up 3, the opposite of up 3 would be going down 3. And instead of going across, go back 1. And again, start from the y-intercept. So if I go back to the y-intercept, negative 1, I'm going to go down 3 to negative 4 and across to negative 1 on the x. And I could do that again, down 3 and across 1. And you notice all 5 of those points line up very nicely. We see the pattern and we can draw the line through them. Here's the tricky part on a computer, is holding my hands steady enough. Oh, I did a good job that time to make that line look nice. So once you see the pattern, you draw the line. It's a good idea to check yourself with these because you really are relying on yourself remembering to go up or down or across or back the right direction. So what I always recommend doing is taking one of the points you just found, for instance 2, 5, and doing a quick check. So if I check that in the original equation, just to make sure I didn't accidentally go up when I should have gone down or vice versa, if I put that into the equation, y equals 3x minus 1, the 5 would be y, the x would be 2. This should give me a true statement. And in fact, it does. 3 times 2 is 6, minus 1 is 5, so I get a true statement of 5 equals 5. Always a good idea to check at least one extra point right at the end before you say that's my true graph. Here's another example, g of x equals negative 1/2 x plus 3. Again, this is a linear equation. It is written in slope-intercept form. So let's match up the slope and the y-intercept. The slope, which is the number that multiplies x, is negative 1/2. And the b is 3, so that means we have a y-intercept at 0, 3. Remember, start with the y-intercept. Graph that because you need an anchor for your line. 0, 3 would be right here. We're going to create the steepness away from that point. Now the steepness is based on the slope. When you have a negative slope, I recommend you put it in the numerator, negative 1 over 2. It's easier for most people to visually see what's happening when you think about the numerator being either positive or negative. So remember I said that if you have a positive number, you're going up in the numerator, and if you have a negative number, you're going down. So what this is saying is I'm going down, and then I'm going to go across 2. So what I'm going to do to create the steepness is I'm going to go down 1 unit and across 2. And I'm going to do that from the starting point. So if I start at 0, 3, I'm going to go down 1 and across 2, and I end up at the point 2, 2. And I can keep doing that as long as I have room. Down 1 over 2, down 1 over 2. I'm kind of starting to run out of room. So remember, you can go backwards as well. The opposite of this would be to go up 1 and back 2. So start at the y-intercept again, go up 1 and back 2, and you'd be at negative 2, 4. Up 1 and back 2, up 1 and back 2. And by repeatedly using a slope, you get a nice grid or a nice series of points pattern across the grid that you have, that you're working with. So once we see the pattern, go ahead and connect it. I'm going to see if I can connect this without having a lot of wobbles. That's about the best I can do on a computer screen. So there we have our graph. Don't forget a quick check. I'm just going to pick out a point here, 4, 1. Let's try 4, 1 as a check. If I do a check, if I put y equals negative 1/2 x plus 3, plug the 1 in for y and the 4 in for x, and calculate, hopefully I get a true statement. Well, 1 on the left. On the right, negative 1/2 times 4 is negative 2, plus 3 does end up giving me 1. So that does check nicely. Again, the reason to check one of those points is that every once in a while we get sidetracked and we go up when we should have gone down or across when we should have gone back. Checking a point will just confirm the entire line graph.